Okay, so we're working on box B here. We're looking at the scalar or the Cartesian equation of a plane here. And just like we did with the vector equation, I think a good place to start is to remind ourselves of what this scalar equation of a line looked like. So the scalar equation of a line was just ax plus by plus c equals 0. And the important thing that you could get out of the scalar equation was if you took a and b, these two things were the normal vector to the plane, to the line. Scalar equation of a plane is going to be very, very similar. I've got a little picture of a plane down here. Again, the plane is being represented by this gray rectangle that I've got here. And keep in mind, whenever you see a picture of a plane, they'll often use a little rectangle like this. Remember, the plane goes off to infinity in all four directions. Okay, so they just show you a little chunk of it, but really it extends off forever and ever. And what we do with the scalar equation of a plane here is, again, we're going to use the normal vector, which in this case is a vector that is perpendicular to the plane, to generate our scalar equation. So if we've got the normal here, they give it as ABC. We're going to use, to be consistent with what we did with lines, we're going to use capital A, capital B, capital C to be our normal vector. The scalar equation of the plane is completely analogous to the equation of a line. We're going to have ax plus by plus cz, because now we're working in 3 dimensions. We've got x, y, and z. So we need another letter here, capital letter D, to be that constant that c was before. Okay. And there's our scalar equation, with a, b, and c being the normal to the plane. So let's take a look at a couple of questions here where we're going to work with that equation a little bit here. And specifically, what we want to be able to do is, if we have the scalar equation, find the vector equation. If we have the vector equation, we want to be able to find the scalar equation. All right. So, first example, we're given the vector equation. R equals 4, negative 2, 5, plus S, 1, 1, 4, plus T, 1, 4, 3. I think that's the vector equation that we were working on in the previous unit. Let's find the scalar equation of this plane. So what we can get right away from our vector equation is we can get these 2 direction vectors that lie in the plane. And I'll just call these D1 and D2. What we want to be able to find in order to get the scalar equation is we need a vector that is perpendicular to the plane. So if both D1 and D2 are direction vectors for the plane, that means they must lie in the plane. So we want a vector that is going to be perpendicular to both D1 and D2. Exactly, we take the cross product. So our normal vector is going to be the cross product of D1 and D2. Okay. So we would set up our little table here, and then we would work out the individual components. I'll just tell you that the cross product of those two is 13, 1, 3. Okay. So now we can go ahead and, because this gives us A, B, and C, we can start setting up our scalar equation here. So this was AX plus BY plus CZ plus D equals 0. We can do negative 13x plus 1y plus 3z plus D equals 0. Okay. Now, we want something that we can sub in for x, y, and z. Well, fortunately, the vector equation gives us a point that we know is on the plane, 4, negative 2, 5. So we can sub those values in for x, y, and z. So we'll have negative 13 times 4 plus our y is just going to be negative 2 plus 3 times 5 plus d equals 0. And we can just solve this thing for d. We can do all this math in our head, and we get d equals 39. Okay. Once we have d, well, we can just go and write our equation. So our equation is going to be negative 13x plus y plus 3z plus 39 equals 0. And there's our scalar equation. So again, this is completely analogous to what we did in for lines when we were doing scalar equations of lines. We found our normal, we subbed in the values of a and b for our normal, then we subbed in the point that we knew was on the line, we solved for the constant, and that gave us our scalar equation. What's a little bit different is going the other direction. Okay, we've got the scalar equation of the plane here, x plus 2y plus 7z minus 3, and we want to find the vector equation. Now there's a bunch of different ways you can do this. What I'm going to show you is the method that I think the textbook uses, but they don't show you an example of it. But using this method should get you the answer that the textbook gives you for the questions that it asks you to do. Okay? And the way to think about this is, you've got your scalar equation, you want to get to your vector equation. Let's first try to get the parametric equation. Okay. So parametric, of course, has the three equations in terms of our two parameters. So it's going to be x equals, y equals, and z equals. So let's first try to get from this to an expression for x. Okay. So you just want to take this and, yeah, not a direction vector at this point. We just need from this, we need something that is an expression for x. Okay. Now, it's not going to be x that you start with every time. We're starting with x for a reason here. Okay, and I'll tell you what it is in just a minute. But if I want to get an expression for x from here, I'm just going to rearrange this expression to solve for x. So x is going to equal positive 3, bring the 3 over to the other side, minus 2y, minus 7z. Thanks. So why did I choose to rearrange this for x first? Well, if I had chosen to rearrange for y, which I could have done, I would have had to divide everything by this 2, and then I would have ended up with fractions, and I don't like working with fractions if I can avoid it. So I can avoid it in this case, so I chose to solve for x, just because it was the easiest thing to do. So that's one part of my parametric equation. I also need expressions for y and z. And I also need two parameters, s and t. What I'm going to do is I'm just going to let y equal one parameter and z equal my other parameter. Okay? So my other two variables I'm just setting equal to my two parameters. How does this help me? Well, let's rewrite this now. X is going to be positive 3 minus 2y, but y is just s here. So we'll do minus 2s minus 7z, but z is just t. So I can now write x in terms of my two parameters s and t. Now, y is just equal to s, but I can interpret that to mean that it's going to be the constant here would be 0 plus 1s plus 0t. Okay, just throwing in these 0 terms that were canceled out when we first, that didn't appear when we first wrote it. And for z, we can do the same thing. It's going to be 0 plus no s and 1t. Okay? Once we've got this, it should be pretty clear how we can get our vector equation. We just pull out the coordinates of the point that's going to be on the line, 3, 0, 0, plus s times, well, let's see, what gets multiplied by s? Negative 2, 1, and 0. And what gets multiplied by t here? Well, negative 7, 0, and 1. And there's our vector equation for that plane. Okay, so the next application of the scalar equation that you'll see is an application that you should be familiar with from when we did scalar equations of lines. And that is, when we're doing lines, we did the distance from a point to a line. Here we're going to do distance from a point to the plane. And completely analogous to what we did with scalar equations of lines, when we're working with scalar equations of planes, the distance from a point to the plane is given by this big long expression here. We're in the numerator, we're taking the absolute value of the scalar equation with the coordinates of the point subbed in. Down in the numerator, we're essentially finding the magnitude of that normal vector. So there's a big complicated derivation of how you can get this equation here. If I were you, I would just, you already know the one for lines. Remember the one for planes too and be able to apply it. Okay. So for an example here, we want to find the distance from the point 1, 2, 3 to the plane negative 13x plus y plus 3z plus 39 equals 0. So that's the plane that we worked so hard to get the equation of 2 questions ago. So we just need to use this formula. So I'm just going to write the whole thing out again. dy plus cz plus d divided by the square root of a squared plus b squared plus c squared. And let's just start subbing things in here. So up in the numerator, we're going to have negative 13. Let's fix that a little bit. Negative 13 times 1 plus our y is just 2, then plus 3 times 3 plus 39. And we want to take the absolute value of all that stuff. Down in our denominator, we're going to do the square root of negative 13 squared plus 1 squared plus 3 squared. And you work all this out. You get the magnitude of 37 divided by the square root of 179. And taking the square root, the magnitude of 37, of course, just gives us 37 over 179. And we're done. Okay. So last thing I wanted to talk about is just a little introduction to talking about two planes. Okay? So let's say we have two planes in 3 dimensions. If we're talking about them, we have 3 possibilities here. They can be coincident, in other words, they're the same plane. They can be parallel and distinct, or they can be intersecting. Okay? So you see a picture here of parallel and distinct planes. You see a picture here of 2 planes that are intersecting, and when 2 planes intersect, their intersection is a straight line. Now these 3 possibilities, you should sort of realize, are completely analogous to what we had when we did the intersection of 2 lines in 2 dimensions, way back in grade 10, right? You could have skew lines if you had 2 lines in 3 dimensions. Okay? You could only have skew planes if you had another 4th dimension, all right? So we don't have the possibility of having skew planes here. Okay? Yeah. The one plane is on a train leaving New York, and another plane is on a train leaving, and they just don't match up or something like that. They miss each other somewhere in the middle. Yeah, so these are 3 possibilities. Okay, same possibilities we had way back in grade 10 when we did two equations of lines. Okay, so the 2 we want to focus on today are how can we tell if they are parallel and distinct? How can we tell if they are coincident? And here's how we can tell. 2 planes are parallel if their normals are parallel, or if the normals are scalar multiples. So if we have the normals of both of these planes, we can really easily check to see if they are parallel or not. And then once we know whether or not they're parallel, we can check if they're coincident. And they're coincident if they are parallel and a point from one plane is on the other plane. So this was the same method we used when we were working with 2 lines to see if they were coincident lines. We took one point from one line, checked to see if it satisfied the other equation. The other option we have for seeing if they're coincident is if we are given the scalar equations of both planes. If the scalar equations are scalar multiples of each other, that means the planes are coincident. Okay? Which makes sense. This is, again, analogous to what we saw with lines. If one line was a multiple of the second line, they were essentially the same line. Okay? So these are sort of the possibilities that we have here. Okay. So here's an example. Determine if the 2 planes intersect, are parallel, or are coincident. Now, if they intersect, we are not going to find the intersection. We're going to leave that until the next lesson. We are just going to check and see which of these 3 situations applies here. So when we're labeling planes, what I'm going to use is I'm going to call one of them plane 1, and I'm going to use the Greek letter for P for one of them, and the other one we will of course use, we'll call this one plane 2. Okay, so plane 1 and plane 2. Now, if we had both scalar equations, we could just check to see if the scalar equations were scalar multiples of each other. Unfortunately, we don't. What we have are one scalar equation and one vector equation. We still want to be able to do this comparison. The way we can do this comparison is we can look at what is easy to get from each of these 2 forms of the equation. So from our scalar equation, what's the obvious thing that we get from the scalar equation? Sorry? Yeah. So let's get our normal here for plane 1. Our normal is just going to be 9, -3, -5. We can check to see if these things are parallel if we can compare this to a normal from the other plane. We can't easily get the normal from the other plane. What we can easily get are our 2 direction vectors. 2, 1, 3 and 0, 5, -3. There are 2 ways we can go from here. Okay? One way is we can figure out what the normal is for plane 2. And we can get that normal by doing the cross product of our 2 direction vectors. because our normal has to be perpendicular to the plane. Our two direction vectors have to lie in the plane, so the normal has to be perpendicular to both of these vectors. So let's do the cross product here. D1 cross D2. And we work this out, and we get negative 18, 6, 10. And then we can compare these two normals. And what we see is that normal 1 is a scalar multiple of normal 2. Because if I take normal 1, multiply it by negative 2, I get normal 2. Okay? Normal 1 is, I'll just write this out here. So it's a little easier to see. So this tells us that, hey, the normals are scalar multiples. Which means the two planes are at least parallel. P1 and P2 are parallel. Now, I said there were two ways we could go once we had the normal and the direction vectors. The other thing that we could have done is, what we're checking to see is if this normal is perpendicular to both of these direction vectors. The other way we have of checking to see if vectors are perpendicular is to do the dot product. So if we did normal 1 dotted with direction vector 1, I should say or, we only have to do one of these, and normal 1 dotted with direction vector 2, and both of these worked out to be 0, that would tell us that our normal is perpendicular to both of the direction vectors. Essentially the same information. So if we do that, what we get is our normal is 9, negative 3, negative 5. If we dot this with our first direction vector, which is 2, 1, 3, lo and behold, we get 18 minus 3 minus 15, 0. Same thing over here. 9, negative 3, negative 5, dotted with 0, 5, negative 3. We get 0 minus 15 plus 15 equals 0. So this would show, again, the normal from 1 is perpendicular to both of those direction vectors, so the planes are parallel. So that's just a little bit of an aside there. Now we have to see if they are coincident or not. Are P1 and P2 coincident? Question mark. And what we want to do is we want to find a point that is on one of these planes and check to see if it satisfies the equation for the other plane. This is where having the vector equation comes in handy because it gives us a point that is on one of the planes. It tells us, just by looking at it, that the point 1, 4, negative 2 is on plane 2. So 1, 4, negative 2 is on P2, or in plane 2. Let's check to see if this set of this point also satisfies plane 1. So let's just sub it into plane 1. And we'll just sort of do a left side, right side check here. So we had 9, negative 3, and negative 5. Okay, and our constant was 20. And the right side was 0. and let's just work out what this is. We get 9 minus 12 plus 10 plus 20. 9 minus 12 is negative 3, plus 10 is 7, plus 20 is 27. So our left side and our right side do not agree. So this point, 1, 4, negative 2, is not on plane 1. So the two planes are not coincident. Therefore, they are not coincident. So they must be parallel and distinct. So plane 1 and plane 2 are parallel and distinct. So that's one way of doing this. Now, as an aside here, if we had been given the two scalar equations, what would this question have looked like? Our scalar equation for plane 1 is what we were given, 2x plus, oh, sorry, that's the wrong question. Our scalar equation to plane 1 was 9x minus 3y minus 5z plus 20 equals 0. We know how to go from the vector equation to the scalar equation, so if we had done that procedure and gotten the scalar equation of plane 2, we would have found that it was negative 18x plus 6y plus 10z plus 14 equals 0. Okay? Where you'll recognize A, B, and C from the normal that we found by doing the cross product. So what we can see is, if I take 9 times negative 2, I get negative 18. Negative 3 times negative 2 gets me 6. 5 times negative 2 gets me 10, okay? Which essentially shows me that these two planes are parallel, because these three terms, A, B, and C, represent the normal of my plane. So the normals are scalar multiples of each other, but if I multiply by negative 2 here, I don't get 14. Okay, so it doesn't work here. So the normals are scalar multiples. The equations of the planes are not scalar multiples. So how can we say this? We can say that k times p1 does not equal plane 2, so they are not coincident. So it's a lot easier if you're given two scalar equations. So you got options here. You could have given the vector equation, found the scalar equation, and then done this, or you can work with the vector equation and do the analysis that we did there. Okay? And that's where we're going to end for today.